3.
Hi dear students, this is me Ishfaq Riaz, and today we'll be discussing an important and interesting topic in physics, that is basically the applications of the Gauss's law. And today we'll discuss third application of the Gauss's law, that is how to find electric field intensity due to a uniformly charged spherical shell. Dear students, you already know what is the statement of the Gauss's law. This is simply electric flux through a closed surface. By definition, it is equal to the surface integral of the electric field, and by Gauss's law it is equal to 1 by epsilon naught times the net charge enclosed by the surface, right? So I will be using this statement to find out the electric field intensity due to a hollow sphere, uniformly charged hollow sphere. If you remember well, we have so far applied the Gauss's law for line charge and for the plane sheet of charge. If you remember, the electric field intensity due to line charge, it is equal to lambda divided by 2 pi epsilon naught r, where lambda is the linear charge density. And one more application we discussed was a thin sheet of charge. So for thin sheet of charge, electric field intensity is equal to sigma divided by twice epsilon naught. So these two applications we have already discussed, where sigma is the surface charge density. So today I will apply the Gauss's law to find the electric field intensity due to a uniformly charged spherical shell. Remember, this is hollow sphere basically, ठीक है ना? So let me consider a hollow sphere here. So let me consider a hollow sphere having center O and radius R. Dear students, try to follow the steps, and I will be applying this Gauss's law to find the electric field intensity due to the spherical shell. So suppose plus Q is the charge that is distributed uniformly over the surface of a shell. Remember, this plus Q is distributed on the outer surface of the shell. And one thing more, there is no charge enclosed by the spherical shell as it is hollow sphere, right? So I will be discussing three cases here. So case first is basically when the point P lies outside the spherical shell. So let me consider a point P here that lies outside the spherical shell, and let me try to find out the expression for electric field intensity due to this spherical shell at point P. So case second will be simply when this point P lies on the shell, and third case will be simply when this point P lies inside the spherical shell, right? So I will be deriving the expression for case first, that is when point P lies outside the spherical shell. So P lies outside the shell. बात समझ आ रही है ना? So when the point P lies outside the spherical shell. Now to evaluate the surface integral, I have to draw a Gaussian surface. So let this be the spherical Gaussian surface at this very point P, right? And you already know by symmetry the electric field intensity at every point on the Gaussian surface it is same, and the magnitude of the electric field intensity is normal to the Gaussian surface. So this will be the electric field intensity at point P, whose magnitude is constant, uniform here at every point on the surface of the Gaussian surface, and at every point it is normal to the Gaussian surface. Now, simply applying this Gauss's law, the electric flux through a closed surface, it is equal to surface integral of E electric field, and this is basically equal to 1 by epsilon naught times the net charge enclosed by the Gaussian surface. So this is the Gaussian surface here, and at around this point P, I will choose a small area element ds, and this is the direction of this area element, that is n cap. It is simply outward drawn normal. Now let's try to evaluate this surface integral at this point P, which lies outside the spherical shell. Now this by definition E dot ds, it is equal to E ds cos theta, and it is simply equal to 1 by epsilon naught times q, where q is the net charge that is enclosed by this Gaussian surface, right? Now you already know what is theta here. It is the angle between E and ds. Electric field, it is perpendicular to the Gaussian surface. This n cap, it is the outward drawn normal. So n cap is this theta is 0 here, and we already know cos 0 is equal to 1. Now electric field intensity at point P is uniform, so I can take it out of the integral. So this is integral of ds. So this is 1 by epsilon naught q. You are getting it now? So this is E. What is integral of ds equal? It is equal to s. So this is 1 by epsilon naught q. What is this s? It is the surface area of Gaussian surface. You are getting it? So what is surface area of Gaussian surface equal to here? So this is 4 pi r square. Right? So let me substitute it here and I will get the expression for electric field intensity due to a spherical shell at point P which lies outside the spherical shell. So E into, so what is S equal? This is the surface area of the Gaussian surface, that is equal to 4 pi r square. So this is 1 by epsilon naught times q. तो हमें E की एक्सप्रेशन निकालनी है. So this is 1 by 4 pi r square epsilon naught q. Let me rearrange this expression. So this is 1 divided by 4 pi epsilon naught q divided by r square. What is this r? It is the distance of the point P from the center of the spherical shell. So this is small r basically. So we are discussing this very case where ये जो capital R, small r है, it is greater than the capital R. Capital R is basically the radius of the spherical shell, and this small r, it is the distance of the point P from the center of the spherical shell. That is why I have used the small r here. So S is basically the surface area of the Gaussian surface. This is simply equal to 4 pi r square. Now remember this expression. This is electric field intensity. Isn't it same that as that of the point charge? If you remember well, electric field intensity due to a point charge is basically equal to 1 by 4 pi epsilon naught q divided by r square. We got the same expression for electric field intensity due to a spherical shell. So for points outside the spherical shell, if this point P lies outside the spherical shell, it behaves just like a point charge, as if the whole charge is concentrated at the center of the spherical shell. So the expression for this electric field intensity due to a spherical shell and the expression for electric field intensity due to a point charge, it is same for the points which lie outside the spherical shell. So for points outside the shell behaves as if the entire charge lies at the center of the shell. So this was the case first, that is electric field intensity due to a spherical shell for points that lie outside the spherical shell. Now the case second will be simply, so let us discuss case second now. What will be the case second? When point P lies on the spherical shell. So P lies on the shell. I mean, when this small r, it is equal to capital R. You are getting it? So I will get the expression for electric field intensity simply. So this is 1 divided by 4 pi epsilon naught q divided by r square. This is the expression for electric field intensity due to a spherical shell when this point P lies on the shell, because here R is basically equal to R. So in this very case, this will be the maximum electric field for spherical shell. Now, one thing more, if I put this spherical shell in a medium of dielectric constant K, then the expression for E will be simply 1 divided by 4 pi epsilon naught K, because epsilon by epsilon naught, where K is the dielectric constant, it is equal to K. So in a medium, it is equal to K times epsilon naught. So here it is once again Q divided by R square. So this will be in a medium, this expression will apply in a medium which has the dielectric constant K. So this is the expression for electric field intensity due to a spherical shell on the when point P lies on the shell. So at this very point, the electric field intensity is maximum. So case third will be simply when point P lies inside the spherical shell. Now let's try to simplify this expression. So case third will be simply when R will be less than R. What does this mean? Point P lies inside the shell. So when point P lies inside the shell, let me show you on the diagram. Suppose this is the point P here. You are getting it? So let me draw a Gaussian surface, rather spherical Gaussian surface. Suppose of radius small r. Now, as per the Gauss's law, this surface integral of the electric field over a closed surface, this is equal to 1 by epsilon naught q. Now look at the diagram. What is the charge enclosed by this very surface? It is equal to 0. So net charge enclosed by the Gaussian surface, I mean, because charge only lies on the outer surface of the shell. There is no charge inside the shell. So if charge inside the shell is equal to 0, simply we will get electric field intensity inside the spherical shell is also equal to 0. So the three cases which we discussed today were when point P lies outside the shell, when point P lies on the shell, and when point P lies inside the shell. So inside the shell, the resultant electric field intensity is always equal to 0. Why? Because there is no charge enclosed by the Gaussian surface. Now let's try to discuss these three cases in terms of the surface charge density. बात समझ आ रही है ना? तो suppose sigma is the surface charge density. What is surface charge density equal? Charge on the spherical shell. So this is charge on the spherical shell per unit area of the shell. Area of shell. ठीक है ना? तो sigma किसके बराबर निकलेगा? What is charge on the spherical shell? Suppose this is Q and suppose S, or simply I can say A is the area of the shell. I can write it like this. So this is Q divided by 4 pi r square. This is the surface charge density of a spherical shell. Now ये जो तीन expressions हमने निकाले, let me try to write it in terms of the sigma. ठीक है ना? So first expression अगर आपको याद होगा, so E is equal 1 divided by 4 pi epsilon naught Q divided by r square. ठीक है ना? So E किसके बराबर निकलेगा? So this is 1 divided by 4 pi epsilon naught. मैं लिखूंगा यहाँ पे 1 by r square. What is charge on the spherical shell? In terms of this, so this is 4 pi r square sigma. बात समझ आ रही है ना? तो 4 pi and 4 pi will cancel out. तो यहाँ पे है sigma divided by epsilon naught. This is r square by r square. So this very case is for the point P that lies outside the spherical shell. Now I would like to write this expression for a medium having dielectric constant K. So E first में लिखूंगा. So this is E first. This is equal to sigma divided by K times epsilon naught. This is R square by R square. So this expression is for the electric field intensity in terms of the surface charge density when point P lies outside the shell, but in case the medium here is having some dielectric constant K. So this will be the case first. Now, what about case second? Let me write it here. So case second will be simply what is electric field equal to on the spherical shell. So this is 1 by 4 pi epsilon naught Q divided by R square. तो इसको हम ऐसे भी लिख सकते हैं. This is 1 by 4 pi epsilon naught. Q के बदले क्या लिखेंगे? This is 4 pi r square sigma. ठीक है? So this is 4 pi r square sigma divided by r square. 4 pi और 4 pi cancel हो जाएगा. R square और R square भी cancel हो जाएगा. So this is sigma divided by constant. Now what is sigma? Surface charge density. What is epsilon naught? Absolute electrical permittivity of the free space. So this is constant basically. So constant electric field is produced on the spherical shell in terms of the surface charge density. So this is E second when point P lies on the spherical shell. So in medium, so I will write this expression as this is K times epsilon naught, where K is the dielectric constant of the medium. Now what about the case third? Since there is no charge enclosed by the Gaussian surface, so the electric field intensity will be 0 inside the spherical shell. So these were three expressions for the electric field intensity in terms of the surface charge density. So we are discussing the three cases basically. Let me try to show them graphically as well. So let's try to analyze them. So field inside the shell is 0 and field is maximum on the spherical shell and it goes on decreasing as per the inverse scale law. Now let me show it here. Let's visualize this. Suppose this is a spherical shell having plus Q that is distributed uniformly over it. So this is plus Q that is distributed uniformly over the surface of a spherical shell having center O and radius R. Now see. So variation of electric field intensity with distance. Suppose R is the distance here. Now electric field inside the spherical shell, it is equal to 0. On the spherical shell, basically at this very point, it is maximum and then it goes on decreasing as per the inverse scale law. So electric field inside the shell is 0. It is maximum on the surface of the shell and it goes on decreasing as per the inverse scale law. Now if I plot a graph between electric field intensity and R, what is R? Distance of the point P from the center of the spherical shell. So let's try to analyze the expressions हमने निकाली. Let's try to analyze them graphically. So if this is the origin O and R is the distance of the point P from the center of the spherical shell. Now electric field inside the shell is zero at every point, at all points inside the spherical shell. Electric field is zero because there is no charge enclosed by the surface. Now at R equal to R, I mean the radius of the sphere, electric field becomes maximum. You are getting it? So this is the maximum electric field when R is equal to R. Now, when point P lies outside the shell, electric field goes on decreasing like this. So here E is inversely proportional to R square. Here E is maximum, and you already know maximum electric field is equal to sigma by epsilon naught, and electric field inside is basically equal to zero. You got it? So this is the graphical representation of electric field intensity due to a spherical shell. So in this very portion, at all points within the spherical shell, electric field is zero because Q is equal to zero. Once you are on the surface of the shell, electric field becomes maximum, and this is the maximum electric field. And you already know outside the spherical shell, this electric field decreases as per the inverse relationship. And for points outside the spherical shell, it behaves like as if entire charge is concentrated at the center of the spherical shell. So dear students, I hope you understood one of the application of the Gauss's law, that is how to find electric field intensity due to a spherical shell. So this was all for today's lecture. We'll be meeting in the next lecture. Till then, Khuda Hafiz. Thank you.